Hey everyone, welcome back. In this video, we will try to understand how to translate the formulation of prospect theory into a loss function so that our large language models can leverage this loss function for training purposes. So this is the value function that we have seen in our last video without diminishing sensitivity. So this is how we express loss aversion. So now in the last video, we have already seen that Z naught is our expected salary and Z is the actual salary in our salary example. So when it comes to large language models, we can assume Z naught is expected reward and Z is actual reward. So what do you mean by this? Let's assume there is a question answer pair in your dataset. So now Z is nothing but reward for a given question answer pair. We already know how to extract reward for a given question answer pair. We have seen the formulation in the first video. So now what is Z naught? Z naught is nothing but average reward across all the possible answers for a given question. So for this given question, who discovered penicillin first, there can be lots of possible answers. So we will be calculating rewards for all those answers for this question, and we will be finding out the average reward. And Z naught is our average reward. So now before getting into this equation, let's try to understand how the dataset of KTO optimization looks like. It has three columns: question column, answer column, and a label column. Label column tells if the answer to the question is correct or not. If it is true, that means the answer is correct. If it is false, it means answer is wrong. So now let's try to consider this row. What's your name? Answer is C++ and the label is false. That means this is a wrong question answer pair or it is undesired question answer pair. So for undesired question answer pair, it is always expected that my actual reward is less than my average reward. For a desired or a correct question answer pair, it is expected that my actual reward will be greater than my average reward, right? If you just look at the formulation of average reward, so for this given question, it is average of rewards across all the possible answers. So by default, going by this formula, Z naught value will be slightly less, right? It won't be high, right? Because end of the day, it's average reward. So now for a right question answer pair, my actual reward should always be greater than my average reward. On the other hand, for a wrong question answer pair, my actual reward should be less than my average reward. So now that's what I've mentioned over here. This is for my desired answer. This is for my undesired question answer pair, right? So here I've replaced with the values of Z and C naught with my rewards and average reward. We already know what is negative lambda based on my previous videos. So now in the research paper, researchers has mentioned Z naught term as KL divergence. They did not mention it as average reward, but both are same, right? So now let's quickly look at how both are same. If you have two distributions, P online and P offline, so this is a standard way. This is a standard way of calculating KL divergence. So now I can replace this summation of probability part with expectation. It's a standard notation, right? So now we already know that log ratio of online probability divided by offline probability is nothing but a reward. So we replace this log ratio with reward. So my KL divergence now becomes expected reward, right? It is expected reward. So average or sample mean is a practical estimate of expectation, right? So we estimate the expectation based on average. So that's the reason here I replace my expectation with average. So this is how we equated KL divergence with average reward. But both are same, don't get confused. So now let's come to diminishing sensitivity. So now if we wanted to include diminishing sensitivity, we have to include alpha in our value function. So now for this moment, let's assume Z naught equal to 0. So now if Z naught equal to 0, this is how the function looks like for different alphas. If you carefully see, if alpha is slightly higher, that means if alpha is 1, the curve is linear, right? If alpha is very less, it is slightly S-shaped near the origin. Let's try to list all the properties of this function, right? It's nothing. I've just plotted this value function in the form of graph for different alphas. That's all. So now let's write down the properties of this specific function. If you see, if z is going to infinity, right? Here x-axis is represented by z. If z is tending towards infinity, the value function is concave. What do you mean by concave? This shape is called as concave. So now when z is increasing, the value function is concave in shape. So when will z tends to infinity? Z will tend to infinity only for desired question answer pairs, right? Only when z is greater than z naught, right? Only when z is greater than z naught, uh, I mean to say the shape is concave, right? When z tends to infinity, when will z tend to infinity? Z will tend to infinity only for a right question answer pair, only when it is greater than z naught. So for desired question answer pair, the value function is concave shaped. For undesired question answer pairs, that means when our average reward is greater than my actual reward. If this is the case, so in this case, z not equal to 0. When 0 is greater than z, for undesired, right, the value function is convex shaped. What do you mean by convex shaped? This is called as convex shaped, right? Two most important properties. If z is tending to infinity, that is for good question answer pairs, my value function is concave. For undesired question answer pairs, the value function is convex. That is when z is less than z naught. Also, if you just carefully look at this graph, the curvature depends on the alpha. If, as we have already discussed, if alpha is very less, let's say if this yellow curve, it's slightly more curved than others, right? It is more S-shaped than others. So that means uh, this function is more S-shaped when alpha is less, right? So now there is a big problem with this value function, especially when we add diminishing sensitivity. The problem is this function is not differentiable at z equal to z naught. This is very important. Why? If a particular function is not differentiable, right? So we cannot compute its derivative. If we cannot compute its derivative, we cannot use that function in gradient descent, right? At the end of the day, we will be using gradient descent to fine tune or train our neural networks. So now this particular function is not differentiable at z equal to z naught. That's the first major point. So now when z minus z naught is very, very close to 0, and if alpha equal to 0.5, let's assume alpha equal to 0.5, then our value function becomes z par alpha for z is greater than z naught. So now let's assume if z value is very close to 0, it is 0.000012 par alpha, and we assume that alpha will be equal to 0.5. It's nothing but square root of 0.00012. So now, if we find out the derivative of this, if we find out derivative of z par alpha, especially when alpha equal to 0.5, this derivative will be very, very huge value, right? Because of this very high derivative, there is a very high chance that we might face exploding gradient problem, right? If we have exploding gradient problem, we simply overshoot our minimum, right? If we wanted to reduce our loss, it's very obvious that we'll be overshooting our minimum. So because of all these reasons, I mean to say having alpha is causing training instability. Why it is causing training instability? Because of my exploding gradient problem, and also it is not differentiable at z equal to z naught. Because of all these issues, we need to replace alpha with some other function so that that function also has such kind of properties, right? So what is that function? So we can replace alpha by something called as sigmoid and beta, right? So now this is how I've rewritten my value function by replacing alpha. I have replaced alpha with sigmoid and beta. Why I replace this? Now let's look at the plot of this function. This is how the plot of this function looks like, right? So if you just carefully see, if z is greater than z naught, if z is tending to infinity, my curve is concave, right? It's very clear that my curve is concave. If z is tending to negative infinity, my curve started to become convex, right? These are two important properties that I have. And next important property that I have when I have diminishing sensitivity is the curvature should be dynamic, right? In that case, we have changed or tweaked our curvature with the help of alpha. So here in this case, we will be changing the curvature of my sigmoid using something called as beta, right? If you carefully see, if beta is very less, my curvature is almost like it's not curved, it's pretty linear, right? If my beta is very high, let's say 10, then it is more curved around the origin. So now the curvature part in my original function is being taken care by my beta, and my convex and concave shape of my original function is being taken care by my sigmoid function. So this is how we try to replace alpha in our actual prospect theory with sigmoid and beta. Why? Because alpha is leading to lots of training instability. I hope this is clear, right? So let's come down. So only thing that is missing is lambdas, right? So what is the use of lambda? In our original prospect theory, lambda is really helpful to increase or decrease human experience, right? In case of loss, just because of lambda, we have tried to, I mean to say, we inflated our, we tried to inflate the intensity of experience. So that's the reason we added something called as lambda of L for losses. And we also add something called as lambda of G for gains as well. Why this is the case? Let's assume if someone felt happy, let's say I also wanted to inflate the amount of happiness. I can do that using lambda G, right? If I wanted to inflate the feeling of loss, I can do that by using lambda L. Original prospect theory did not have this lambda G. So the researchers have added this as a part of KTO optimization. So now, what is the loss or sorry, what is the objective function that we have over here? You have to maximize this value function, right? Your model parameters should be in such a way that we have to maximize this value function, right? So why this really makes sense? If you just look at this function for my desirable answer, when this property will be maximum, this property will be maximum for desirable response only when z is much greater than z naught. Only when my actual reward is much greater than my average reward. Only then the first property will be maximum. So when this will be maximum, this will be maximum for a given any undesired question answer pair. If z naught, if my average reward is very high than my actual reward, only then this will be maximum. Right? So whether it is for desirable question answer pair or undesirable question answer pair, my value function should be maximum. That's the objective function. But in general, in machine learning or reinforcement learning, we always tend to minimize loss. So now we try to convert this maximization problem into a loss minimization problem, right? How do we do that? It's a very simple translation. The translation is something over here, right? So if z is greater than z naught, that means for a desirable question answer pair, my loss equal to lambda g minus lambda into my sigmoid function. For undesired question answer pair, my loss equal to lambda L minus lambda L into my sigmoid function. For a moment, let's assume lambda G equal to 1 and lambda L equal to 1. So now, no matter what the question answer pair is, I wanted to minimize this loss. So if it is equal to 1, this equation will get translated into 1 minus sigmoid of beta into z minus z naught, right? If z is greater than or equal to z naught. It is 1 minus sigmoid into beta into z naught minus z if z naught is greater than z. This is for desired question answer pair. This is for undesired question answer pair. So now let's assume for a proper desired question answer pair, my actual reward should be very high, right? If my actual reward is very high, so my sigmoid of a very high value, will be close to 1, right? If it is close to 1, so 1 minus 1 will be 0. This is the minimum value. right? So now let's consider an undesired question answer pair from our dataset. So now if we consider that, my average reward should be much higher than my actual reward. Why? Because it is an undesired question answer pair, right? For an undesired or for a wrong question answer pair, my actual reward should always be very, very less than my average reward. So now if my actual reward is very less, so then sigmoid of my very high value will be high, right? If you assume like it's 1. So 1 minus 1 equal to 0. So this is the minimum value that this loss function can take. So now you need to tweak our LLM parameters. So during training, so the backpropagation happens in such a way that the parameters are tweaked in such a way that this loss is minimized, right? So this is what is mentioned in our KTO research paper as well. Let's quickly go back to our research paper. So this is what is explained over here. You can just have a quick look at it. It is exactly what I explained. So I think pretty much that's it for this video. See you in the next one. Bye.